So this is the first part of chapter 11 review. We will go over question 1 to question 8. The chapter 11 is on the modern atomic theory, so it emphasizes more on what electrons are doing in the atoms, where they are located, and about that. So let's go over question 1. How frequency and wavelengths of an electromagnetic radiation are related? Give the formula and specify if they are proportional or inversely related. So the formula that relates frequency and wavelengths is like this. C is equal to nu times lambda. So nu is the frequency, lambda is the wavelength. C is the speed of light. And we always use this value of 3×10⁸ meters per second, which corresponds to the speed of light in vacuum. But in air, we typically use that value as well. And that's the maximum value for the speed of light in any kind of medium. Vacuum is a medium that is empty, basically, and so that's where the light will be the fastest. And so the speed of light is equal to the frequency times the wavelength of a given light. If you rewrite this, lambda is equal to C over nu. So you can see from this second equation that lambda and nu are inversely related because lambda is in the numerator and nu is in the denominator, which means that when you are decreasing the wavelength, that means you're increasing the frequency. And frequency goes in the same way as the energy of the light. So the shorter the wavelength, the higher the frequency and the higher the energy of a light. And inversely, the longer the wavelength, the smaller the frequency and the smaller the energy. So question 2, what does it mean that the energy levels occupied by electrons within an atom are quantized? So as we know from this chapter, so we have this nucleus, a very tiny nucleus in a large space. The atom is really very big compared to the size of the nucleus. And in that empty space around the nucleus, you have electrons. And we know from what we learn in this chapter that electrons are not randomly distributed. They are in shells and subshells and orbitals. And when they occupy a given shell or actually a given orbital, they will have a given energy associated with it. So because of that, we said that the energy levels are quantized. It means that the values are very specific. The electrons cannot have any kind of value if you want. It is very specific amount of energy that they possess when they are in a specific orbital. So we call these discrete values of energy, which means it's not continuous. And so I have these drawings to help understand the difference between the two. So the drawing A here to the left here represents continuous energy. So if you look at this drawing, A is just that large purple bar, that goes up in energy. And that includes all energy values from 0 up to the maximum value. Any kind of energy value is allowed in this type of continuous energy levels. That's not how it is in atoms. It's more like in drawings B. And let me just say that the ramp here that varies continuously in elevation is what you would have as an analogy to represent continuous energy levels, right? It's continuous. You have all values possible from the minimum to the maximum. But in the atom, it's not like that. What we have is we have discrete or quantized energy levels, which means that only certain energy states are allowed. And so if you look at the drawing B to the left, you have just single lines at specific values of energy. So the bottom of the energy scale here is where the nucleus is, and so as you go up, the energy increases. So as you go farther from the nucleus, energy increases. And so in the atom, then it would be more like a flight of stairs, the analogy for where the electrons can land. It only allows certain elevation, and so we said those elevations are quantized. You cannot be in between a step, right? Electrons can have only very specific values that corresponds to steps. So that's how you can visualize things to help you understand what it means to have quantized energy levels. So question 3, when lithium salts are heated in a flame, so lithium salts here, you have to imagine a solution where you have lithium compounds dissolved in it. So typically would be dissolved in an alcohol so that you can burn it. So when they are heated in a flame, they emit red light. And here you have, those dishes where you have a liquid that is burning. And so the lithium salt will be the one with the red light. Copper salts are heated in a flame and in the same manner, and they would emit green light. And then the yellow one here would represent sodium salts. So they emit yellow light. So why do we know that lithium salts will never emit green light and copper salts will never emit red light? So we just learned that atoms have quantized levels of energy. And so what happens is, so let me move all of this here so we can understand. So the electrons can only be at those specific energy states or energy levels. And when they are in the ground state, the electrons, when they are in the ground state, we say that the atom is also in the ground state and it's not excited. So if you when atoms receive energy from an external source, they can absorb that energy and become excited. And when atoms are excited, it means the electrons have moved up in energy levels. But the excited states are not stable, and atoms will release this energy by emitting light. So here on the left, we see this drawing where the energy goes up in the y-axis, and we have an excited lithium atom that is represented with the wavy red lines. So that's an atom that is excited, which means electrons within the atom have moved up in the excited state of energy. But it's very unstable to be excited for an atom, and they will want to release that energy. And typically what happens is that it is released in the form of light. And that red wavy arrow here represents the transition from the excited state to the ground state, or any kind of lower energy state. It doesn't have to be necessarily the ground state. It can be any kind of lower energy state than the excited state where they were in. And this energy, the energy difference between these two levels, often, like for lithium, copper, sodium, as we saw in the picture, this amount of energy corresponds to visible light when it's a photon of light. And for lithium, it's a photon, it corresponds to a photon of red light. So this amount of energy corresponds exactly to energy for a red light. And so that's why we see the flame being red when we are burning lithium. When we are burning it, it excites the atoms, and then when they go back to their lower energy state, they will show a red flame. So here the emitted energy is carried away by a photon of a specific color that depends on the energy difference between the excited state and the ground state. So here I want to emphasize it's not necessarily down to the ground state. It's a lower energy state. And so in the case of lithium, the emitted light is red because its energy corresponds to photons of red light. And so copper will emit a photon of green light because the energy difference between its excited state and its ground state is larger. So if you see here this diagram on the right, for example, a copper atom would have, so be aware that between lithium and copper, the energy values will be different. So for every atom, the energy values that are allowed are different for each of them. So that's why they will emit different colors because they are all different. And that's a thing we can use to identify metals. Metals are identified by the color they burn in. So that's useful for, it's been very useful for chemists. Okay, so that answers question 2 or 3. Question 4. Differentiate among the terms energy levels, which are also called shells, or sublevels or subshells, and orbitals. So these are 3 different levels of, compartmenting the electrons. And so give the symbols for each and the maximum number of each. So I have this figure to help you really understand the difference between shells, subshells, and orbitals. Let's go over this. It's a big figure here. So, okay, a shell is the first way to compartmentalize the, regions where the electrons are roaming around. So shell, typically we tend to imagine them like spherical envelopes that you add around the nucleus and you add up by, going farther away from the nucleus. But the shells, they contain subshells. In the first shell, there is only one subshell. In the second shell, there is 2 subshells. In the third shell, there is 3 subshells. And then in the fourth shell, there is 4 subshells. And as you go up in shells, there is a maximum of 4 subshells. So here in this shell, we have 2 subshells. So that's why we have the 2s and the 2p's. And so within the subshells, there are then the orbitals. And that's the ultimate, you cannot go farther than that. And the subshells are of different kind. There is the S, the P, and the D, and the F. And the S subshells, and orbitals are spherical, so just like spheres. The P subshells are a dumbbell shape, like you see them here. And then the D subshells, there is 5 of them, and they have, dumb shells perpendicular to each other in the different planes of the, the 3D structure. So, okay, let's go over the way it's organized. So I told you in the first shell, and this is represented by the principal quantum number n. So we call them principal energy levels or shells. They are represented by n, the principal quantum number. And there is up to 7 level, up to 7n. And so in the first shell, there is only one subshell, and that's the S. And in the S subshell, there is only one kind of orbital, and that's the, 1s here. So then in the second shell, there is more subshells. There is 2 subshells, right? The number 2 here tells you there is 2 subshells, the S and the P. Again, the S orbital, it's only one spherical orbital, and then you have the 3 p orbitals, and we identify them by 2px, 2py, 2pz. So in total, in the level 2, there is 1, 2, 3, 4 orbitals, right? 2 subshells, but 4 orbitals in total. Then in the shell n equals 3, there is 3 subshells, because again, that number tells you the number of subshells. The S, the P, and the D. Again, one orbital s only, 3 p orbitals. So they are named 3px, 3py, 3pz. Let me emphasize that the 3 in front here refers to the shell number, right? And then there is the 5 d orbitals. There is 5 d orbitals. For example, there is the 3dxy, there is the 3dxz, 3dyz, etc. So in the third shell, that means you have 1, 2, 3, 4 plus 5, 9 orbitals, right? So 9 orbitals in the third shell, 3 subshells and 9 orbitals. And then in the fourth shell, there is 4 subshells, the S, P, D, and F. Again, the 4s orbital, you have 3 p orbitals, 5 d orbitals, and 7 f orbitals. So these numbers have to be learned by heart, right? The 7 f orbitals, 5 d orbitals, 3 p orbitals, and 1 s orbital only. So that means in the shell number 4, you have 4 subshells, but let's count them. The 1s orbital plus 3p, that's 4, plus 5d, that's 9, plus 7, that's 16 orbitals in the fourth shell. So that's how it is organized. So question 5, what is an orbital? And we kind of answered that already, right? So how would you define an orbital? So in words, an orbital is that region within the atom around the nucleus where you have a 90% chance or 95% chance, depending on how you set your probability, of finding electrons with a given amount of energy in there. So orbitals have been, they are the solutions of what we call the Schrödinger equation. And so it's mathematical, equations that define a region, and with the center being the nucleus. And when you know that region, there is a 90% or 95% of chance of finding the electron within that region. And the electron will have a given amount of energy associated with that orbital, right? We said that electrons can only have very specific values of energy. And here there is another drawing showing again the p orbitals. Actually I like this because so typically we represent the orbitals as envelopes, but you really have to understand that this envelope is actually representing the 95% of chance of finding the electron inside that space. And so if you look at those p orbitals and then if you look at the left side of the drawing, you see dots, right, that represent the same shape as the dumbbell. It's what we call a density plot. And so this density plot, you can imagine that each dot represents an electron. If we were able to make a picture of the electron around the nucleus, so the nucleus would be at the coordinate 0, 0, 0. So, in the center there where the lines crosses. So the nucleus is there. And then if you would take thousands of pictures of the electrons that are in that 2px orbital, for example, you would see them mainly along the x-axis, gathered on either side of the nucleus. And then as you move away from the axis, it's less and less that you see dots there, right? And so now if you try to make an envelope that contains 95% of those dots, that's how you get this dumbbell shape, right? This corresponds to the envelope that would have 95% of the dots inside, and then 5% would be outside. So sometimes you would find the electrons outside that space. So that's what really orbitals, what they are. So it's, very complicated to draw them like this. And so orbitals, and that's question 6 here, orbitals are represented with a box. And so a box would represent an orbital. And then we draw an arrow up and an arrow down to represent electrons when it's filled with electrons. So what are these arrows representing? Let me just say here that if you have not learned that yet, per orbital, there can be only 2 electrons maximum, right? There is a rule that says there can be only 2 electrons maximum in an orbital. And electrons, they are spinning, which means, they are rotating around themselves, around an axis. And one electron will spin in one direction, and that would be the arrow up. And the other electron that is in that orbital with the first one, will spin on the opposite direction, and that would be the arrow down. So that's why when you have an orbital and 2 electrons maximum in there will always be one arrow up and one arrow down, because they are spinning in opposite directions. Otherwise, they could not be both at the same time in one single orbital. So what these arrows are representing, they are representing the direction of the spin of the electrons. They are spinning, and they're spinning, let's say one is clockwise and the other one is counterclockwise. So be aware that you should always pay attention to the way you draw your arrows. So question 7. In a calcium atom, which electrons have more energy, the 2s2 electrons or the 4s2 electrons? So we've seen how, we start from, if I look here, the nucleus would be below that first shell, right? Below here, at the bottom of that first shell, you have the nucleus. And then the energy goes up as you move from n equal 1 to n equal 2 to n equal 3, n equal 4. So electrons in the 2s2 orbitals compared to the 4s2 orbitals, the 2s2 would be less in energy than the 4s2, right? So the 4s2 electrons have more energy than the 2s2 electrons because they are farther away from the nucleus, right? You need to remember energy increases as you move away from the nucleus. And that's why, when electrons absorb energy, they move up into excited states and they have more energy. So that can be a way to remember this. And question 8, how do we call electrons that are in the highest energy shell? So for each atom, there is a specific number of electrons when it's the neutral atom. And so electrons are filling shells, but they are not filling all of them. And so the highest energy level for a given atom is called the valence shell. Electrons that are in the highest energy level are called valence electrons. This is important to know that term because we refer to those electrons more than to any other electrons. And so they are the highest energy electrons, and they are in what we call the valence shell. Why these electrons are important? It's because they are on the outermost shell. So they are the most accessible. So you can plug them out, remove them from that shell more easily. And you can add more electrons in that valence shell if it's not full. And these electrons in the valence shell are what give the atoms their properties. This is the most main thing that contributes to the properties of the atoms. So that's why they are important, and we will look at those electrons in particular more than the core electrons. All the others are called core electrons, C-O-R-E.